Good afternoon, my student. Welcome to another chemistry lesson. Today we are going to discuss about titration, but specifically bag titration. I found out that most of our learners have a problem when it comes to performing titration experiments. So I will take you through bag titration so that you see where you normally go wrong. But I want to define the meaning of the term bag titration. It is a method of volumetric analysis which is used to determine the concentration or amount of a reactant. It involves reacting quantities of substances being analyzed with an excess amount of a suitable reagent whose concentration and volume is known. Then the excess amount is measured through titration. The amount of the reactant that reacted with the analyte is then determined by subtracting the excess amount from the initial value. Then the data obtained can now be used to determine the concentration or the amount of the analyte. Is it okay? So allow me to take you through the chemicals that I have with me here that are going to help us in this sample experiment. So focus and see. On my right here, I have solution P. This solution B, which is 0.5 molar sodium hydroxide. Then I have solution A. This solution A is 1 molar hydrochloric acid. 1 molar hydrochloric acid as solution A. Is it okay? Then I have a solid here, solid C, a white solid C. It's an anhydrous sodium carbonate. Then I have, of course, an indicator, phenolphthalein indicator, with a dropper, meaning this solution will be used dropwise. Is it okay? Then let us now focus on the board for 1 minute. On the board here I have written bag titration, and this experiment 1.0, and the aim of this experiment is to determine the mass of sodium carbonate in a given solid. Then you are provided with the following solutions. 1 molar hydrochloric acid as solution A. Then 0.5 molar sodium hydroxide as solution B. Then anhydrous sodium carbonate of unknown mass, solid C. And remember, the aim of our experiment is to determine the mass of this sodium carbonate as solid C. That's the aim of our experiment. So the mass is unknown. So after titration, we shall calculate the mass of this sodium carbonate. Then on the procedure, you will allow me to take you through by carrying out an experiment. Is it okay? By carrying out an experiment. So procedure number one, follow me very carefully. And this one requires total concentration and patience. Patience is very important. So I'll take a clean measuring cylinder which is 100 mils. Is it okay? Then I take solution A, which is 1 molar hydrochloric acid. Is it okay? Then I measure 60. I measure 60 of this one. So I have to measure 60. So that is 60 ml of solution A. Then you have to follow this. At the end, when we shall be carrying out the calculations, you will be asked to calculate the number of moles of hydrochloric acid at the original 60. So the original solution I've measured 60. Then the next procedure, I transfer this solution into a clean 100 beaker, 100 milliliter beaker, the glass one. So I transfer the whole of it. Then after that, I take, this is 1 gram of solid C, anhydrous sodium carbonate. So I add into this solution A. Then we make the observation as I add the whole of it. You can hear the effervescence. You can see the gas bubbles. Then you can stir using a glass rod. Until the reaction is complete. That is when the effervescence or gas bubble stops. You have to stir. So I've reacted sodium carbonate with 60 centimeter cube of solution A. Then I have to transfer now this resultant solution into another clean measuring cylinder, into another 100 ml clean measuring cylinder like this. You transfer all of it. Then after that, I have to top up with the distilled water to this solution until it is now 100 mils. I top up with distilled water. Is it okay? So this is my distilled water. Then I have to top up and ensure you don't exceed 100. Exactly 100. Let me go. Yes, it is exactly 100 mils. Is it okay? Then the next procedure, I take a clean 250 milliliter beaker. Then I transfer this solution into this beaker. Is it okay? Then I have to label this solution at 100 as solution P. Is it okay? And also remember, you will be asked to calculate the number of moles of this solution P. That's at 100 mils. Is it okay? I've said at 60 you will calculate the number of moles from the original solution. Then also at 100 you have to calculate the number of moles. Is it okay? The next procedure, I take a clean conical flask. Then using a pipette with a pipette filler, I have to pipette 25 centimeter cube of this solution P into this conical flask. Is it okay? So let us go. So this is a pipette. Then this is a pipette filler. Nowadays we don't use our mouth to suck chemicals for healthy reasons. Is it okay? So don't forget that. So let us now pipette 25 centimeter cube of solution P using a pipette. So this is exactly 25 ml of solution P. So I'm transferring it into a clean conical flask. Like that. Is it okay? Then after that, the next procedure, after pipetting solution P, I have to add there 3 drops of phenolphthalein indicator. Is it okay? Let us go. So I take a dropper and add there 3 drops. 1, 2, 3. 3 drops. Is it okay? Then thereafter, the next procedure, I now fill the burette with solution B, which is 0.5 molar sodium hydroxide. Is it okay? So this is a sodium hydroxide solution. So this one I fill with inside the burette. So I take my sodium hydroxide solution, then I fill the burette. Let us go. You have to fill the burette up to the 0 mark. Remember, a burette has a maximum volume of 50 ml. So you have to fill until it's on the 0 mark, and you have to read below the lower meniscus. Is it okay? Then what am I going to do next? The next procedure, I have now to take this pipetted solution P with an indicator, then I titrate against with the sodium hydroxide in the burette. Is it okay? But initially look at the color of solution P with an indicator. It's a colorless solution. So I'm going to titrate until a permanent pink color just appears. Is it okay? This is how we normally do it. So I put this conical flask on a white tile, that way. Then I'm going to swirl the solution as I titrate, or as I release the sodium hydroxide solution dropwise until a permanent pink color just appears. So your focus now it is on this conical flask. Is it okay? Let us now go. I have now started the titration process, and this is how to swirl. This is how we normally swirl. So concentrate as I swirl. So you concentrate as I swirl until a permanent pink color just appears. Let me continue titrating until a permanent pink color just appears. It's not yet. But it's showing some signs of turning. Yeah, you can now see the pink color has just appeared. And yeah, you can watch and see until that just pink color appears, and then you stop. Then you read on the burette. When I read on the burette, it is 20.8 mils. So if that is the case, you can watch and see the pink color has just appeared. Is it okay? Then you come and record on the titration table. So focus and see on the board. I'm now going to record. So what you do, you have been given this table, and this is part of question 1, completing the table, which is 4 marks. And we have carried out titration number 1. So you are supposed to carry out titration number 2 and titration number 3. So we have the initial and the final burette reading. Then of course volume of solution be used. So in this case, my student, I normally advise this way. When you are carrying out the experiment, always start from 0. Fill the burette with the solution up to the 0 mark. Is it okay for all the titrations? So in this case, titration number 1, we have started at 0.0. Is it okay? So this is the initial burette reading, 0.0 for the first titration. Then the final burette reading, we have found out it is 20.8. Is it okay? So my student, if you carry out the second and the third titration, the difference is very small if you are very careful. So I normally advise this way. When you are filling the titration table for all the titration, ensure at least the values are uniform. Is it okay? That is for consistency reasons. For consistency reasons. Is it okay? So you fill the burette for the second iteration so that you also start at 0.0. So if you are very keen, you will also get 20.8. Is it okay? And if you also carry out the third iteration carefully, you will get 0. You start at 0, then you will get 20.8. Is it okay? This is for consistency reasons. Then, volume of solution B used. Remember, solution B is 0.5 molar sodium hydroxide solution. So how do you get that? The volume of B used. You get the final value minus the initial value from the burette. Is it okay? So for example, if you take 20.8 minus 0.0, this is 20.8. When you subtract the second iteration, you also get 20.8 minus 0.0, that is also 20.8. Similar to the iteration number 3, 20.8 minus 0.0, you get 20.8. Is it okay? Then I want to remind you something on this table. When you are filling the table, it is 4 marks. So this is how the marks are distributed. We have complete table. Complete table, that is 1 mark. Then we have decimal place. This is another mark. Then we have accuracy, 3rd mark. Then we have principle of averaging. Principle of averaging, that's another mark. So in total, you have 4 marks. Is it okay, my student? I'll emphasize something on decimal places. When you are filling the table, ensure the decimal place is uniform. If you are using 1 decimal place, let it be uniform all through. Then if you are using 2 decimal places, let them be uniform. Is it okay? But I normally advise my student that you use 1 decimal place when you are filling the table. Is it okay? It is easier. Then let us move to question B. Determine the average volume of solution B used. Average volume of solution B used. We know the volume which the solution which is in the burette is solution B, which is solution B is sodium hydroxide solution. So the average, you just take the 3 volumes in the 3 titrations, and ensure when you are getting the average, ensure the volumes are consistent are consistent. Is it okay? So in this case, there are how many iterations? 3. 1, 2, 3. So I take, so average volume is equal to 20.8 plus 20.8 plus 20.8. Then I divide by 3. I divide by 3. Why 3? Because we have 3 iterations. Is it okay? Then this one is equal to 20.80 centimeter cube. Then I put there a tick. When it comes to calculating the average volume, my student, it's advisable that you use 2 decimal places. For example, 20.80 centimeter cube. Because if you use 1 decimal place, it means you are sure of the accurate value. So if it is not an accurate value, it's advisable that you use 2 decimal places. Is it okay, my student? Thank you. Then the next question, C, calculate the number of moles of sodium hydroxide. Solution B. Solution B, watch. It is 0.5 molar sodium hydroxide. Are you getting? Solution B. So when you want to get the number of moles, we normally say that from our formula. Number of moles is equal to molarity times volume all over 1000. Is it okay? So 1000 is a constant, which means the volume in 1 liter. Is it okay? So what's the molarity of sodium hydroxide? So this 0.5 molar is the molarity. Is it okay, my student? Just see how easy it is to calculate this. So you take molarity, which is 0.5 times volume. Volume of solution B used. Solution B used. So it is the average volume. Is it okay? Solution B used, it's the average of the 3, which is 20.80. So that's the volume that we use here. So it is 20.80. Then you divide this one by 1000. So if you calculate it very carefully using a calculator, I can see that is 0.0104 moles. Are you getting it? 0.0104 moles. Is it okay? Then we want to move on to part D of the question. Let me push aside these things so that we have enough space. So that we have enough space. I want to look at part D of the question, where we are saying find the number of moles of hydrochloric acid in 25 centimeter cube of solution P. Remember, we pipetted 25 of solution P. Is it okay? And that solution P was the one now in the conical flask. Is it okay? Which has reacted with sodium hydroxide from the burette. So we look at now the reacting ratio, mole ratio between sodium hydroxide and hydrochloric acid. And we have to write down a chemical equation. Is it okay? So let us see. Sodium hydroxide, that was sodium hydroxide reacting with solution P, which is hydrochloric acid. So a reaction between a base and a dilute acid, you always form a salt plus water. A salt plus water. So what's the name of the salt? This is sodium chloride. The salt is called sodium chloride. Then of course plus water. Then after that you have to balance the chemical equation to give you the mole ratio. So sodium 1 on the reactant side, sodium 1. Oxygen 1 atom, oxygen 1 atom on the product side. Hydrogen there are 2. Hydrogen there are 2 on the reactant side, then hydrogen there are 2 on the product side. Balance. Then chloride, you have 1 chloride atom on the reactant side and 1 chloride atom on the product side. So the equation is balanced. Then we look at now the reacting ratio, the reacting mole ratio. So you find that we have 1 mole of sodium reacting with 1 mole of hydrochloric acid. So the mole ratio is 1 to 1. So you write here and say mole ratio between the base and the acid is ratio 1 to 1. Is ratio 1 to 1. So 1 mole of sodium hydroxide react with 1 mole of hydrochloric acid to give those products. Is it okay? So if we know the moles of sodium hydroxide that reacted with the hydrochloric acid, then the moles are equal because they are reacting with the mole ratio of 1 to 1. So moles of sodium hydroxide equals to the moles of hydrochloric acid. Is it okay? Thank you. So this means moles of, let me write properly. This means moles of sodium hydroxide solution equals moles of HCl, which is equal to, so we have found out that just a minute, we have found out that the moles of sodium hydroxide solution be used, which reacted with HCl, we have calculated it is 0.0104 moles. So these moles equals to the number of moles of hydrochloric acid that reacted with sodium hydroxide. So I transfer the same here and say, slowly please, I transfer them here and say that is equal to 0.0104 moles. Then I put tick there. Is it okay? So writing the equation is very important, and you will find out that in this case we are going to write two chemical equations. Then I move to part E of the equation. You can focus clearly and see my student. Determine the number of moles of HCl, the chloric acid, which is solution P, in 100 centimeter cube. In 100 centimeter cube of solution P. In 100 centimeter cube of solution P. So you ask ourselves, moles of hydrochloric acid in 25, we have found out it is 0.0104 moles. So we say that if 25 centimeter cube, volume of solution PHCl is giving us 0.0104 moles. What about 100? What about 100 centimeter cube? this one will give us which moles. Is it okay? So this one requires patience. We just now cross multiply, as simple as that, isn't it? So you take 0.0104 divided by 25 centimeter cube times 100. If you calculate this one carefully, this one gives you, I can see 0.0416 moles. Then I put a tick. So you just relate, if 25 of HCl is giving this one, what about 100 of the same solution P, this volume? How much will it give us, isn't it? Is it? So it is 0.0416 moles. Is it okay? Then we move on to part F of the question. Calculate the number of moles of HCl in original 60 centimeter cube of solution P. Of original solution P, which is also 2 marks. So remember I told you when I was carrying out the procedure that in that original 60 you will also be asked to calculate the number of moles. Is it okay? So we know the volume is 60. So we apply the formula again. These simple formulas. Say that. So you say that number of moles is equal to molarity times volume all over 1000. All over 1000. That's the formula always. Number of moles is molarity times volume of 1000. Where 1000 is a constant, means volume in 1 liter. Is it okay? So we just substitute the values there. So what's molarity of the original solution? Solution A. The molarity is there, hydrochloric acid. The molarity is 1 mole, 1.0 mole. So you just substitute. So the molarity capital M is 1 times volume. We are talking of volume in the original 60 centimeter cube. Is it okay? So you put there 60. Then you divide by that constant, which is 1000. That means a volume in 1 liter. Is it okay? So if you calculate carefully, I can be able to see that is 0.06 moles. Then I put a tick if you calculate carefully. Is it okay? Hope you are following and you are enjoying the working, isn't it? Good. Let us continue. We are almost coming to an end. Then question G. Calculate the number of moles of hydrochloric acid that reacted with the carbonate. Number of moles of hydrochloric acid that reacted with the carbonate. So it is very simple. So you take the number of moles of hydrochloric acid at the original 60. Are you getting? At the original 60 centimeter cube. Then you subtract the number of moles of hydrochloric acid at 100 centimeter cube. Are you getting, my student? So let us go. So the number of moles at original 60, we have found out it is 0.06 moles minus the number of moles of solution P or HCl at 100 centimeter cube, we have found out it is 0.0416 moles. So I subtract that one. 0.0416 moles. So if you subtract, let me see, this one, subtract this one, that is, okay, that is 0.0184 moles. You can also follow me with your calculator step by step. Is it okay? So you get 0.0184 moles. Then lastly, the last question on the same H, question H. Determine the mass of sodium carbonate that reacted with the acid. Mass of sodium carbonate that reacted with the acid. So this is another reaction between the acid and sodium carbonate. So you have to write down a chemical equation. Is it okay, my student? Let us go. So we have sodium carbonate. Sodium carbonate solid reacting with dilute hydrochloric acid. That is in the original solution A. Then, from the basic knowledge we know, when a carbonate reacts with a dilute acid, you form three products: a salt, water, and carbon dioxide. So what's the name of the salt will be formed between hydrochloric acid and sodium carbonate? The salt is sodium chloride, isn't it? That is sodium chloride. The salt is sodium chloride. Then plus water. Then plus carbon dioxide gas. So always remember to write the correct state symbols, and you balance the equation for it to qualify to be a correct chemical equation. So let us balance. We have two sodium atoms on the reactant side, then we have one sodium. So I have to balance by putting here 2, to balance the sodium ion. Then chloride ion are now 2, so I have also to balance this chloride ion on the reactant side. So I have to put here the 2. Is it okay, my student? Then why am I writing this chemical equation? So as to get the mole ratio in which the carbonate and the acid they are reacting. So if we have balanced correctly like this, so it means 1 mole of the carbonate is reacting with 2 moles of the acid. Is it okay? So the mole ratio, the mole ratio here is, we have 1 for the carbonate, then we have 2 for the acid. So the mole ratio is 1 to 2. Is it okay? Then the question is this: determine the mass. It is all about the mass. Determine the mass of sodium carbonate that reacted with the acid. So we need to know first of all the number of moles of the acid that reacted with the carbonate. Then we use the mole ratios to get the number of moles of the carbonate that reacted with the acid. Then the number of moles of the carbonate and its relative formula mass, RFM, will enable us now to calculate the mass of sodium carbonate. Let us go. What are the number of moles of HCl that reacted with the carbonate. We have calculated in G. Number of moles of hydrochloric acid that reacted with the sodium carbonate is 0.0184 moles. Is it okay? So we relate this way. If ratio 2, that is of the acid, is how many moles? This one, 0.0184 moles. What about ratio 1? What about ratio 1 for the carbonate? What about 1? Ratio 1 will give us how many moles? It's now all about cross multiplication, isn't it? So if you do it very correctly, it is 0.01884 divided by 2 times 1. This one gives us 0, let me see, that is 0.002 moles. Is it okay? So those are the moles of the carbonate that reacted with the acid when we use mole ratios. Is it okay? Then the question is asking us to calculate the mass of sodium carbonate that reacted with the acid. Now we apply this formula. Mass is equal to relative formula mass, that's RFM, times number of moles. Is it okay? Is it okay? Then, therefore, our mass, what's the relative formula mass of the carbonate? You calculate. Just look and see. The relative atomic mass of sodium is 23, and there are 2 atoms. So 23 times 2, 46. Carbon is 12. So 46 plus 12, that is 58. 58, isn't it? Then 3 atoms of oxygen, and each atom has a relative atomic mass of 16. 16 times 3, 48. 48 plus 58, that is 106. So that is 106. That's the RFM of sodium carbonate. Then times number of moles. What are the number of moles of the carbonate that reacted with the acid? We have found out it is 0.0092 moles. So I substitute 0.0092. So if you calculate this one, let me see, 106 times 0.0092, that is 0.9752 grams. You can even round off to a whole number, which is around 1.0 gram or 1 gram. Is it okay? So we have come to the end of the lesson. So in summary, my student, I want to show you how back titration is very simple and how calculations on back titration are also very simple. Is it okay? So in this case, from the beginning, you are given 3 reactants, 2 solutions and 1 solid. And that is the characteristic of most of the back titrations. Is it okay? And you are going to have 2 reactions taking place. Two reactions taking place. One, we have found out solid C, which is the carbonate reacting with hydrochloric acid. Then, during titration, we are also seeing sodium hydroxide solution reacting with the same hydrochloric acid. So it means solution A, which is hydrochloric acid, was the one in excess. So some amount reacted with the carbonate initially at the beginning, then the remaining HCl in that resultant solution P, it is now reacting with sodium hydroxide. Are you getting that? So hydrochloric acid was the one in excess. So when it comes to calculation of number of moles, we calculate the number of moles in the original solution at 60 before we reacted with the carbonate. Then after reacting and topping up with the distilled water to 100 mark, we have also to find the number of moles at 100 ml. Then we pipetted 25 centimeter cube of solution P. So you have found out that we also calculate the number of moles at 25. But that one, we look at the mole ratio between the base and the acid. So if we use just the mole ratio to get those moles, then we relate. If 25 is giving us this mole of solution P, what about at 100? Then at 60, we have calculated, you have seen. Then to see the number of moles of HCl that react with the carbonate, we now subtract the one at original 60, we subtract at 100, which we have found out it is 0.0416 moles. Are you getting? So my student, it is simple as that. Hope you have enjoyed the lesson. But in the next lesson, I want to assure you, I'll also do the same. Thank you. And maybe you are wondering who is this? I'm called Mr. KW, a teacher of chemistry. Thank you. Thank you.